Let's explore the clock latency. The starting point of the clock signal is the clock source, where the clock source is the origin where the clock signal is generated, which can be either a PLL or an external oscillator. Then the clock propagate from the clock source to the clock definition point, where the clock definition point is the reference point in a circuit where the clock signal is formally defined for timing analysis and distribution. To better understand the clock definition point, consider a hierarchical design where we have multiple people working on multiple partitions or the submodules. The block owner would define a clock at the port of the block. This port is called the clock definition point. Finally, the clock signal propagates from the clock definition point to various sync points within the design, where sync points are typically the clocked elements such as flip-flops. So, we conclude that the clock signal experiences a time delay between its generation at clock source and its arrival at different sync points within a digital circuit. This time delay is known as clock latency. So, we can define clock latency as follows. Clock latency refers to the time delay taken by the clock signal to travel from its source to various sync points within a digital circuit. Clock latency has two components: source latency and network latency. During the travel of clock signal from the clock source to the clocked elements, it encounters two stages of delay. First stage is the delay from the clock source to the clock definition point, and this is called source latency. And second stage is the delay from the clock definition point to the clock pin of a clocked element, and this is called network latency. Therefore, source latency is the time taken for the clock signal to travel from the clock source to the clock definition point. Source latency, also referred to as source insertion delay. In other words, it measures the delay between the clock generation and the point where it is defined within the circuit. It is influenced by factors such as the clock source's driver strength and the load capacitance it drives. Source latency could represent either on-chip or off-chip latency, depends on the clock source. Let's illustrate. On-chip clock source, where the clock generator located within the chip, such as a PLL. Off-chip clock source, where the clock generator located outside the chip, such as an external oscillator or a clock signal provided by another system. Now let's see the network latency. Network latency is the amount of time the clock signal takes to travel from the clock definition point to the clock pin of a flip-flop, latch, or any clocked element. The network latency includes the delays introduced by various elements in the clock path, such as buffers, wires, and clock distribution networks. Every sync point in a circuit has a different network delay based on the location of the sync point from the clock definition point, leading to variations in the clock path. Overview. The total latency is the sum of source and network latency. Both types of latency are critical for timing analysis and must be carefully managed to ensure that the digital circuit operates correctly and meets its timing requirements. Designers should aim for a balanced clock tree with consistent source latency and network latency throughout the design. This can be achieved through careful clock tree synthesis and skew balancing techniques. I hope you found this video helpful. Stay tuned for upcoming videos where we'll explore more topics related to IC design.